afternoon, everybody. So thank you for coming to the last seminar that we have on the Robotics Center Seminar Series for this term. So it's a great honor and pleasure to have here Professor Cynthia Sung. So she's a Gable Family Theorem Assistant Professor in the Department of Mechanical Engineering and Applied Mechanics. So I'm from the Grass Lab at the University of Pennsylvania. So she received her PhD in electrical engineering and computer science from MIT in 2016, and her BS in mechanical engineering from Rice University. And she's a recipient of multiple awards, such as the ONR Young Investigator, the NSF Career, and many others. So, yeah, thank you for coming.
Great, thank you very much. Thank you, everyone, for coming. Really wonderful to be here and meet all of you. And thank you for inviting me here and showing me all of the wonderful work that's going on. I'm excited today to share the work that our group is doing in origami-inspired design, and to show you some of the cool things that you can do with folded systems. So I guess before I get started, how many people here have done origami? Just show of hands.
It depends what the origami.
A fair number of people. So sometimes I get the question, what is origami, right? So origami is the art of paper folding, right? It's a art that's been around for centuries, right? And it's the idea that you can take a flat sheet of paper and then add creases to it and then turn the sheet of paper into an interesting 3D shape. So this here is a video of me folding a pretty traditional model, a paper crane. Right, and just through the sequence of adding folds to the sheet, we get an interesting shape that looks like a bird, but we can also get these structures that move, right? And so in this case, the way that the folds are added allows us to also create this flapping wing design, right? And we're interested in origami from this point of view, that we can make interesting 3D structures, that we can make them move. And the other interesting thing is that if I then take this model and then I unfold it, then I get a network of folds onto a piece of paper. And this pattern of folds, where all of the dashed lines here are places that got creased on this paper, directly map to the 3D shape. And so there's a direct correspondence between what the final shape is that got created and this network of folds on the paper. And so we're interested in taking this idea of folding and bringing it into robotics, right? So there's a lot of evidence that origami is a useful tool in engineering design. Oftentimes, people use it for its ability to create deployable structures, for its ability to create lightweight structures. What you're seeing here is a smattering of examples of where people have taken this idea of folding and put it into some sort of engineered structure. This one here is a deployable lens. The one on the right is an architectural structure where they've put shades on this tower to prevent or allow light to go into the building. And in all of these cases, origami has been used as a tool for allowing shape change, and in the case of this chair here, to bear loads with a very lightweight structure. So we want to know whether we can take advantage of the same sorts of properties for robotics. So in robotics then, the question is, how do I use folding and use it to do work? Right, so what you're seeing here are examples of this sort of idea where people have folded structures, and that folding creates a robot that can then move. And the one on the top is fuzzy, but it can either actively deploy structures. What you're seeing on the top right is a manipulator arm. At the bottom, you see these crawling structures. And the act of folding allows us to both assemble these robots very quickly by fabricating them out of planar fabrication processes and then folding them into shape, but then also to continue to get these robots to move after they're folded. So in my group, we're interested in the question of, well, how do we take, or what are the underlying design principles? How do we actually design these sorts of origami-inspired machines? And this is not a new question. There's a whole field of origami mathematics. And in this field, people have been primarily concerned with the question of shape. How do we create different types of 3D shapes? And what we now know in this space is that actually if you take any polyhedron, so any simple polyhedral mesh, then there are algorithms that will automatically generate the fold pattern for these shapes. And so we know that these algorithms will generate the desired mesh and that they exist. And now there's software that you can download where you just take whatever mesh that you want, input it into the software, and out comes the fold pattern. So I want to show you an example of one of those. So this is the Origamizer here. This was an algorithm that was developed by Tomohiro Tachi back in 2010. What you're seeing on the top right is the interface for this software. The input here is the Stanford bunny. It's a pretty common pattern in graphics, a mesh in graphics. And on the right is the corresponding fold pattern that was automatically generated by the software. And what you see in the middle is Tomohiro folding this pattern. So you can see the light changes in the background. It takes him about 10 hours. But at the end of this entire process, I'll fast forward a little bit, he ends up with this bunny shape, right? And so what we know is that for any simple polyhedral mesh, this fold pattern on the right does exist. And it'll take a little bit of work to actually fold the pattern that comes out, but you can generate these shapes, okay? So when it comes to robots, though, I want to take a little bit of time to complain a little bit about these algorithms because they allow us to create 3D shapes, but they're not necessarily practical for robotics, right? So what I have here is the mesh on the left, and on the right is the fold pattern that got generated. And the coloring is a little bit off here, but these triangles that are white are the triangles that are on the exterior of this mesh. And all of the material in the middle, these kind of trapezoidal parts that are supposed to be colored gray, are material that gets tucked away. So in the video that you saw from Tomohiro folding this structure, you saw him doing a lot of pinching and a whole bunch of binder clips. All of that was him tucking away these extra creases here. The strategy behind this algorithm is we take all of the triangles on the outside of this mesh, spread them out on the paper so they don't intersect, and then tuck all the extra material away, right? And so there's actually a huge amount of wasted material on the sheet that we fold into the 3D structure. In addition, there's a question of what is the mapping between the 3D shape that we're generating and the fold pattern, right? So it's not entirely clear what this triangle on the bunny corresponds to on the fold pattern, right? And if I decide that I want to change the shape of the bunny, maybe I want to make the ears longer or I want to make the body shorter or something, it's not clear what I need to do on the fold pattern side in order to make that happen, right? And so normally what you would do if you're interacting with this software is you would modify the mesh and then just run the algorithm from scratch, right? There are additional issues which are, I don't know if I'm using these sorts of algorithms, since they're focused on geometry and shape, they don't necessarily create structures that move, right? And so they're not as useful for robotics, right? And then there's another question, which is, well, if I also want these structures to do work, if I want them to carry loads, or if I want them to be able to apply forces, then because these algorithms are geometry focused, there's no real notion of how much force or how much structural integrity they have, right? So when it comes to our lab and this idea of making origami-inspired robotics, then what we care about is, well, the question of not just shape, but also motion. So what are the underlying design principles for making origami-inspired devices that can also move? And we tackle this idea from a couple of different directions. In our lab, we do a lot of work in computational robot design, that is creating representations, algorithms for software or algorithms that allow us to construct these sorts of designs computationally. We do a lot of work in origami-inspired fabrication, right? Because origami is also made of thin sheets, then oftentimes they're compliant, so we do some work in modeling and experimenting with compliant mechanisms. And because origami structures also create devices, origami structures can also change shape, then a lot of our work also involves reconfiguration. And so combining all of these ideas together, then the big question we think about is how can we more formally think about origami-inspired design in the context of creating new robot functionality? So today what I wanted to do was share a few of the projects that we're working on in this space. The first thing that I wanted to show you was some of the recent work that we've been looking at where we're dealing with the question of payload or force generation, where we've been interested in the mechanics of origami structures and how well we can design them to do work. We've also been thinking more theoretically about the question of how do we design origami structures to create mechanisms with arbitrary kinematic complexity. And then because a lot of these structures do take a long time to fold, so I told you that the video at the beginning took Tomohiro 10 hours, well, we also think about fabrication processes for creating structures that can self-fold so we can make the fabrication easier. And then we take these ideas and then we apply them in a few different spaces. So my plan for today is to go through each of these and show you some of the work that we've been doing in any of this space. Before I do that, any questions or comments?
Yeah, I have one question.
Oh, yep.
You touched upon this, but when I design robotics, I care about shape, but I also care about material selection.
Yep.
Because I need to carry the information from geometry and micro properties of the material to macro properties.
Yep.
Is that being put into that?
So it's not something that we're actively working on right now. We do collaborate with people in material science who are thinking specifically about that problem. From our point of view, we're interested in, well, once you have the material, what can you do with it? So how do we manipulate the mechanics by manipulating the geometry?
Because quite often people do 3D printing, and they get beautiful shapes, but they cannot tell me anything about the structure. And as an engineer, I worry about
Yes.
various kinds of tensors and stress and all that stuff.
Yes, for sure. So in this case, we often fold our robots out of PET plastic for prototyping, but we've also experimented with other materials, metals, carbon fiber. And in what we're looking at is the geometry as a tool.
But in item 1, you must be touching upon this, right?
What's that?
In item 1, you must be touching a little bit about that.
We're touching on how do you control the stiffness using geometry. So once the material has already been chosen.
Material is given, okay.
Yeah.
Right, thank you.
Okay. Other questions? Okay, so that's a good lead-in to this question of the first bullet point, though. So what you're seeing here is, again, some examples of origami robots that people have been created. This is from a review back in 2018, so it's a little bit old at this point. But I think the observations still stand, that most of these structures here are made out of like paper or thin plastic. And so most of them are also quite small, right? And so when I was starting as faculty at Penn, there was a big question that was, well, what is it that origami robots can actually do? Because if they're all restricted to be like this big and they can't actually bear any loads, then they're not that useful. They're just going to be toys, right? And so one of the first things that we tried to tackle in our lab was proving that these sorts of structures could actually be useful. So our main application that we decided to tackle was the idea of running and jumping. We decided that this was one of the more challenging tasks that we could try to tackle in robotics, but also that origami could be useful for. So what you're seeing here is an old video, 1980s, of one of the first hopping robots that Mark Rayburn has become famous for. And the idea here is that if we want robots to be robust, to be able to do agile locomotion, the key is the robot's ability to manipulate energy, right? So in this case, these legs here are acting like springs. They're storing energy and they're releasing energy in order to get the robots to do this hopping motion. And if that is the way that the robot operates, then the controller itself can actually be quite simple, right? Because the mechanism is doing most of the work. And so there are models that show that these sorts of robots and also many biological creatures can be modeled and controlled as these sort of spring-like systems. And so we wanted to know whether we could use origami-inspired structures to do similar types of maneuvers, with the idea that if we used origami-inspired structures, then they would be more lightweight, and we could take advantage of fast origami-inspired fabrication. So we started to become interested in origami structures that could bear loads. And this is an example of a pattern that we became very interested in studying. It's a bellows pattern. And our main inspiration here was the bellows theorem, which is this idea from computational geometry. It's a conjecture. It was first conjectured in the 1970s and not proven until the 1990s. But the idea is this, that if you have a polyhedron and it has rigid faces, then even when the polyhedron flexes, so the angles between the faces change, the volume remains constant, right? So the way to think about this is, for example, when you have a cardboard box, right? Usually when you flat pack a cardboard box and then you unpack it into box shape, right? When you're doing that unpacking, the volume inside of the box is changing, but the top and bottom faces are also changing shape, right? So in that case, the volume is changing, but the faces are also flexing. Once you fold the top and bottom faces down, then the box becomes rigid, right? Then the volume becomes fixed. So the implication here is that if you have a polyhedron and you want to change its volume, then inherently the faces have to flex, right? And because materials resist deformation, then now what we can do is actually use the flexing of the faces, a geometrical parameter, in order to estimate the mechanics response, right? So in this case, this is the bellow, the folded bellows that you see at the top. It's quite stiff, and I have one here so you could play with it. This one is just folded out of 5 mil thick PET. And the idea here is that by changing the fold pattern and even just a single parameter, this alpha here, you change the 3D geometry and you change the amount the faces deform when you compress the entire structure. So even by changing a single parameter, this alpha, by something as small as 1 degree, then you get large changes in the mechanical response. And you also see different types of behaviors such as snap through and buckling. And these are behaviors that you can tune by changing the geometry, not necessarily the material. Now, of course, if you wanted to scale the entire stiffness, you would change the material, right? But you can change this just by changing the geometry itself. So my students got very excited by this, and so they decided to fold a whole bunch of these structures and characterize them. And so what you're seeing here are force displacement curves that they measured on an MCS machine. And there's, even with the same material that we're folding the structure out of, by changing the angle of the fold that we're creating, we can get up to 3 times change in stiffness of the structure itself. And by nesting these structures, we can get orders of magnitude of stiffness change. And so what that means is that now we can design the parameters of these structures in order to create the sort of stiffness of spring that we want. So what you're seeing here then is the result of this idea. Right here on the bottom of this robot here is that spring, the one that I'm passing around, this time tuned so that it has a stiffness of 3 kilonewtons per meter. And this robot here uses the exact same controller as the Raybert hopper that I showed you at the beginning, but in this case, the spring for this robot is being implemented as an origami structure, right? What I want to emphasize is that in this case, the robot is carrying 3.5 kilograms of mass at the top, which is just motors, frame, computation, etc. And all of the energy that is being stored and released for this jumping behavior is being stored into 50 grams of folded material. And so despite the fact that we're using folded structures and thin shell structures for these robots, they can actually be quite strong. So I often also get the question of how long these structures can last, because maybe they're subject to fatigue. So the students also did cyclic tests on the structures. A nice thing is that because we're taking advantage of facial deformation in order to create stiffness change, not necessarily the stiffness of the folds themselves, then these structures can last quite a while. In this case, what you're seeing is 2,000 cycles of compression and tensile tests. And the first cycle is going to be a little bit different from all the other ones. That's a pretty well-known phenomenon. But the cycles quickly converge to a steady state behavior, which is this blue curve here. And that behavior lasts over like 1,000 cycles. This exact same bellows that we tested was then the same one that we put on the robot that I showed you on the previous slide. And so that spring that we tested has lasted another few thousand cycles just through demos that we do as we bring people through the lab. Now, in addition, because these structures are compliant, we can also implement other, hopping controllers on this robot. We can change the angle of the touchdown, and now we can control the velocity at which the robot moves forward or backward. And again, because the structure is compliant, this robot can move over different types of terrain with no change in the controller itself. So this robot here, the students set up an obstacle course for it. In this case, it's just going to hop over these small obstacles. And the velocity is going to change, right, because it's not responding to the environment, but it is able to jump and hop successfully over these environments. All of this is being done with no change in the controller itself.
Can I get rid of the road?
Can you what?
Can I get rid of the road?
You could, and then we would have to do more feedback. So in this case,
Gordon Chang in Germany has put sensors on the bottom of the feet,
yep,
which I did not know that is important for even us walking, and he was able to go without the road by sensing the force from the bottom of the feet and then adjust.
Yep.
Is that possible?
It is possible. So in this case, we have only a single sensor in the foot, which is detecting contact with the ground, and that's it. If we added additional sensors, not right now, no. But if we added those extra sensors, we'd be able to take off the rod.
Because then you could jump over the V's.
Yes.
You can make bigger jumps or smaller jumps.
Yes.
Okay, thank you.
Other questions? Okay. So these ideas also, oh, go ahead.
Just have I see it slows down when it goes over the anchorage boom.
Yep.
And is that, I guess, why is that?
So right now, when it's slowing down because the character of the ground has changed, right? So the ground is now soft, which means the ground is also now absorbing energy, right? And so that energy is not necessarily going into the robot jumping, and we haven't changed the controller at all. So so that affects the robot's velocity.
You try to play volleyball in the sun, can you jump the same as if it is asphalt? No, right? Because the same problem.
Right. Other questions?
Okay.
Okay. So these same sorts of ideas are also applying to other spaces. So for example, if we take a look at not the bellows, but this magic ball pattern, we can do the same process of characterizing what is the force response when we deform the object. In this case, when we compress the ball, then it changes in volume. And so we can use this. We can, again, compress this structure in order to change these volume changes. And now we have a different robot than when we put it in the water. It creates a jet that propels it through the water. So the underlying mechanism behind this robot is the same as the jumper. We're just doing this compression and then quick release. But because we can control the mechanics and the shape change of the origami device, we can use it in other ways. And in this case, what we've shown is that by taking advantage of the mechanics of the origami pattern in this way, we can get low cost of transport. In this case, the amount of energy that our robot consumes is approximately the same as squids of about the same size. So
Could you make it so that this operates like a squid, that I have a fold-up device that has a vacuum, and then in addition to the expansion, I can actually push the water back?
yeah, so in this case, that was the main idea, actually, that we were inspired by squids. What you're seeing in this video here is that when we compress, it's not playing, but when we compress the ball, it expands in volume, so that sucks the water in.
Okay.
And then when we release, then the ball very quickly contracts, and that creates the jet that pushes the
That's it
robot.
from the figure. Okay, yeah.
Yeah.
Okay, thank you.
Other questions? Yep.
Have you done any comparisons of this to more traditional materials like rubber? If you got a rubber device.
Yeah, so this is a question we get a lot about, whether we've compared to other soft materials. We haven't done a formal comparison yet, but what we've found just anecdotally is that rubber is often much more dense, so it's heavier and much more dampy. And so you lose a lot more energy into the material than you do if you use an origami structure. That's just anecdotes. We haven't done the formal analysis. Did you have a question?
Yeah, I guess I'm just curious if you've done any work on like the speed of the actual like actuation, because like this is a very like slow expansion, and then if you've done anything like changing the speed, because if it's very stiff, that can like use a lot of force.
Yep. So in this case, we've done some tests with how much you contract the robot, and then the frequency of contraction and release. We haven't played around with the speed of contraction. But we recently got funding from ONR to do that sort of experiment. So in the next few years, we should hopefully know more about how the robot is interacting with the water, how we can optimize the mechanics of the skin in order to, create more energy efficient locomotion. Okay, great. So we decided that with this demonstration in this study, that we had basically shown that origami structures were not necessarily any less capable than more traditional robots when it came to energy storage or when it came to force generation. And so another project that we've been working on is then trying to think about what are the degrees of freedom that we can then embed into origami structures. So the question here is, how do we create fold patterns that have different degrees of freedom or different kinematics? And I'm trained as a computer scientist originally, and so, of course, the first thing that we need to do is define our exact problem. And so the problem that we defined here was given a Dynamic-Hardenberg representation, how many people are familiar with DH? Okay, only a couple. So Dynamic-Hardenberg representation is basically one of the standard representations for manipulator arms in robotics. And the idea is that for every degree of freedom on a serial manipulator arm, I can describe that degree of freedom using 4 parameters, which basically tell you the location and orientation of the axis of motion. So in this case, this is a revolute joint here. We have rotation around this axis, which we called Z1. And so I can describe the location of Z1 relative to the origin using 4 parameters. And then the Dynamic-Hardenberg representation is a table of those parameters for every single joint on the arm. So that's high level. If you're interested, then there are all sorts of interesting explanations for
You
the
have
details.
relative motion in 3 dimensions?
Yep.
All 3 Euler angles?
Yes.
Joint?
Yep. So the problem that we decided to solve was, given the Dynamic-Hardenberg representation, the standard representation of serial manipulator arms, is it possible to automatically generate a crease pattern that it folds into an arm with the specified kinematics? And what we decided to do for this problem was to take a modular approach. So going back to my complaints at the beginning about the Origamizer, the virtues of a modular approach are that now I create a database of origami modules. And then when I want to construct a serial manipulator arm, I basically just connect those modules to each other, right? Now it becomes very obvious which parts of this arm correspond to what parts of the fold pattern, because all of the modules are self-contained, right? And so if I want to take a modular compositional approach to design, I need to basically answer 2 questions. One is, what are the modules that go into this database that I can use to construct these manipulator arms? And then how do I combine them together, or how can I guarantee that they can be combined together? So Wei Shi is the PhD student who worked on this project, and he basically created this database of 4 modules, parameterized modules, one for rigid translation, rigid rotation, a translational joint, and a rotational joint. And each of these modules is parameterized to give you a particular amount of translation or rotation, and the fold pattern changes accordingly. Now, with these 4 modules, then, if we can figure out how to combine them together, then we can basically create any rigid transformation, right? Because any 3D rigid transformation is just a combination of rotation and translation. So now the question becomes, how do I combine them together? And what we were able to show was that we could automatically construct these fold patterns. The main insight here was that the DH specification only locates your degrees of freedom, not necessarily your joints, right? So if I have my arm here, I have an elbow with an axis of rotation right here, right, that allows my arm to rotate. It doesn't actually matter whether my elbow is here or whether it's over here, as long as the axis of rotation is down this line, right? And so I can take advantage of this extra degree of freedom in order to do design for this arm, right? So what we were able to show is we were able to create a provably correct algorithm that automatically generates tubular crease patterns for structures with arbitrary kinematic complexity in polynomial time. And we did this by mapping the design problem onto a Dubin's path planning problem. And this part here was really exciting because Dubin's path planning is also a problem that is very well studied in robotics. It's basically the way that you plan for cars or fixed-wing aircraft, right? And there's decades of work in this space. So if this mapping is correct, then that means that people who are doing kinematic design for manipulator arms can now take advantage of decades of work that people have already done in computational geometry, and they don't need to reprove all of these results from scratch.
Is the duality rigorous here?
What's that?
Is the duality rigorous here?
Is the what?
The duality.
The duality? What about it?
How do you map them one to the other?
Oh, I'm going to show you.
Because it must be going through some dual process, right?
There must be what? Sorry.
Through a dual process, like Lozano duality or anything like that, no?
Not really. It's pretty one-to-one.
But it's rigorous.
Yep. So the idea is this, that we have these modules that we've added in our database, right? This is a rotational module. This is a translational module. And let's say that there are 2 joints that we want to connect on our arm. So I can try to construct a Dubin's path between these 2 joints that I'm connecting together. So if I'm able to construct a CSC path, that is a path that consists of circular arcs and straight lines, then each component of this path gets mapped to the center line of one of these modules, right? So I can directly convert this path into a sequence of origami modules that then fold into the rigid link. Now, I know from the Dubin's path planning literature that this path exists as long as the joints are sufficiently far apart from each other, right? And so what I can do is take advantage of the extra degree of freedom that we found in the DH specification to move these joints farther away so that we can construct these CSC paths, and then we can directly construct this origami pattern, right? So in this way, we've shown that as long as you have a DH specification and this extra degree of freedom, then we can use existing path planning approaches to always to construct a collision-free and correct origami pattern for this sort of mechanism. And so what you're seeing here is that process of moving the joints farther apart, and now every component of this path is being converted into the corresponding fold pattern, which then folds into a 3D structure that basically follows this path. So what you're seeing now is the equivalent folded mechanism. And these parts here, this one, and that one, are the rotational joints. And their axes of rotation are in exactly the right place according to
The
the original
distances are
specification.
controlled by the curvature?
What's that?
The distances, how far apart you have to be, are controlled by the curvatures?
Yes.
The same as in the path.
Yep, exactly.
So you cannot do things like that. You have to do like-
No. No. So we haven't yet proven anything about how compact this structure can be. So what we've shown is that as long as you can solve the path planning problem, right, then this origami structure will exist. What happens is that because we're putting some constraints on the path itself, we sometimes end up with these weird winding paths. So this would be the center line of a mechanism that got automatically generated by our algorithm for the Puma arm that you see in the top right. And it's quite long. If we ignore some self-collision constraints that we also added to the problem, we get a path that looks like that. Neither of these are great, right? But if we ask a human to do the job of designing the path, then we get a much nicer mechanism that looks like this. And so what we're working on right now is first trying to figure out what are the lower bounds in linkage size, but then also trying to figure out whether we can take the output of our algorithm and then post-process or optimize it to get something more like that. Yep.
So it's the same question as before. This is all geometry.
Yep.
Now I want to understand how would I build an arm that can lift certain weight and so on and so forth. And then the problem of composability is more difficult because every one of these geometric elements is going to have some parameters which are subject to specifications from the material properties. And then how I put them together is a big problem.
Yep.
Any attempt in that regard?
Yes. Let me finish this thought real quick and then I'll get to your question.
I'm sorry, I'm ahead of. Okay.
No, it's fine. It's fine. So just to finish this thought, this code for what I showed you is on GitHub. So if you ever decide that you want to make your own origami arm, you can go to this link, pull our repo. It's all in MATLAB, but you can input your own DH specification and try out the fold pattern yourself. So I'm going to skip ahead a little bit to answer your question. So there was then an attempt on our side to figure out, well, can we combine these two ideas together, right? So what I showed you at the beginning was this jumping robot where we said, well, we can change the stiffness of the origami pattern by changing certain geometric parameters. And then now we can design origami patterns with potentially arbitrary degrees of freedom. But the second part was only a kinematic analysis, right? And so the question is, now can we combine these two ideas together in order to create kinematic structures that also have pre-prescribed stiffness profiles, right? And so one thing that I want to note is that all of the joints in our database are also parameterized for stiffness. And so we can manipulate the rotational or translational stiffness of each of the joints in the mechanism by changing its geometric parameters. And so one thing that the student tried to do then was say, well, let's make now a multi-degree of freedom robot. This is a quadruped now with 8 joints on it. He designed where all of the joints need to go, dropped that specification into our algorithm and said, okay, now automatically design the fold pattern. I want to get a multi-degree of freedom hopper. He put motors onto the structure, and then this is what he got. So it is possible to create these sorts of multi-degree of freedom origami, but then also dynamical robots. Now, you may be looking at this and thinking to yourself, well, this is not quite answering the problem or quite answering the question, because if you look closely, the motors on this robot are placed exactly where the joints are. And so actually the motors are doing the work of delivering the necessary power for jumping, and we're not actually relying on the origami or the energy storage into the structure in order to create this jumping the way we did in the first demo, right? And so what we've started to think about now is, well, if we have this sort of structure, how do we figure out what the stiffness parameters are that need to be in every joint, right? And how do we combine the design of the kinematics of the structure with the mechanics of the structure? And so my student Shivangi has started to look into this problem where we've started to think about what can we do if we have the ability to change the local stiffness of compliant structures. What you're seeing here is basically a spring network representation of the sorts of structures that we're thinking about. In this case, we have 3 segments. Each of them has 6 springs on it. And this blue line is a tendon down the middle that you can pull. Okay? When you pull this tendon in a similar way to the way we pull the tendon on the leg in our jumping robot, then this structure will deform in a way that depends on the stiffness distribution, right? So in this case, when I pull the tendon, the spring over here is softer than the spring over here, so the bottom segment, bends to the left, opposite for the segment on the top, right? And you can change how this structure deforms by changing the stiffness distribution, right? We can predict how this structure is going to deform by looking at the energy landscape, right? And so in a quasi-static scenario, then basically the entire structure is going to tend towards the configuration of lowest energy, right? And so I can write a matrix equation that describes what the force balance is for this structure. And what's interesting is that I can construct this matrix analytically, but I can also differentiate this matrix and, as a result, the potential energy in the system with respect to the stiffnesses, right? So what we've started to do now is think about, well, if I want this structure to deform in a particular way and I want it to store a particular amount of energy, how do I design the stiffnesses along the structure? And we've discovered that you can do that using basically gradient descent on the stiffnesses themselves, right? So we've proven that this gradient descent approach is stable. It'll bring you to a local minimum. It's not going to bring you to a global minimum, but the system isn't going to go crazy. And so what you're seeing here is a simulation that Shivangi put together where this is, again, our 3-segment compliant structure. Each of these colored lines is a spring. The thickness of the line over here tells you its stiffness. So thinner lines are softer, thicker lines are stiffer. And then over here, you're also seeing graphs of how the stiffness change. There's a tendon down the middle, which is not drawn, which is compressing the whole structure. And as the stiffnesses change, according to our gradient descent-based controller, then the entire structure is bending and converging to the purple triangle that you see up there. And so what we've shown now is that if we have these springs or the stiffness profile for this manipulator arm or leg that we potentially want to build, then we can either pre-design using gradient descent-based optimization, or potentially in the future we can change on the fly the stiffness distribution along the structure to produce the sorts of deformation that we want. Not only that, but because these structures have way too many degrees of freedom, then you can also have independent control over the equilibrium configuration and the stiffness, right? So what you're seeing here is that I can uniformly scale the stiffness of all of the springs along the length of this structure, and the equilibrium configuration does not change, right? But the stiffness or the force response that you experience at the end effector does change, right? And so now you can take advantage of these extra degrees of freedom to independently design the kinematics and the force response of the structure.
Any thought of going to smart materials so you can actually control?
Yes.
Because
So
I can make every spring a smart material and I can control it overall.
yes, you've predicted our next work. So basically, the idea now is that we have these controllers, right? We have our design algorithm. So first thing we're going to do is verify that they work just from a pre-design standpoint. But then we're working with a material scientist, Shu Yang, at Penn, who does a lot of really interesting work in liquid crystal elastomers and dielectric actuators to try to see whether we can take her materials and then embed them in a distributed fashion into these sorts of structures and try to implement these algorithms in real time. And then what can be really exciting is that for the jumping robot I showed you before, if you imagine this as the leg, now we can deal with situations like what you brought up at the beginning, which is we can then start to get the leg to respond to different grounds and stiffen or soften in order to get the robot to be more energy efficient. So that's the long-term vision. Other questions? Yep.
So for each ligament there, for each supporter, is the stiffness constant throughout the deformation, or is varying? Because if you're compressing it, the stiffness might vary itself.
Yeah, so in this case, we assumed just linear stiffness. It's not necessary. It's not. So right now, what we're trying to do is extend our analysis to nonlinear springs. And it doesn't seem like it's going to cause us too many issues, but we still have to see. Yeah, no problem. Other questions? Okay. So then our other direction that we've been thinking about for this work is from the point of view of fabrication. And so a lot of the structures that I just showed you are quite complicated. And even the students in my lab who are very experienced folders by this point take about 2 to 3 hours to fold each one of them, right? And so in the future, if we want to make these sorts of robots a practical reality, then we need to get them to fold themselves, potentially. And so my student, Gabe, has been working on magnetically controlled systems for us to be able to get structures to self-fold over folding sequences of arbitrary complexity. So those of you who have seen self-folding systems before probably know that they are usually folded like under heat or, humidity or something, and there's one global signal that you send into the pattern, and then everything folds at the same time. That's not going to work for many fold patterns, right? Because a lot of fold patterns are complex and they need a particular sequence of folds to happen. So we wanted to make sure that the system that we designed could deal with more complicated fold patterns. So what you're seeing here is the system that we've been working on. The idea here is that we take a magnetic sheet and we equip our system with a magnetic write head. This magnetic write head works very similarly to the way that the hard drive on your computer works, where now if we apply a strong enough magnetic field to a portion of this sheet, we can overwrite the magnetic signal. So we can write the magnetic polarity of every single pixel on this sheet down to millimeter resolution, right? So this here that you're seeing on the right is now a magnetic image of the program that we've written onto this sheet, where blue is south-facing pixels and then red is north-facing pixels. And when we expose this sheet to an external magnetic field, then we can get this structure to self-fold. And the way that the structure folds is going to depend on the interaction between what we've programmed on the sheet and what the external magnetic field is. So this is an example of one of the sheets that we've created. This one is programmed. So if you fold it in exactly the right way, it'll stick to itself. So you can play around with it. And you can figure out how to exactly to fold it. But here is a video of this system at work. In this case, we're folding a cup pattern. It's a pretty popular pattern among lower school students. And what you're seeing on the right is the magnetic program that's being programmed onto the sheet right now. Again, south is blue, north is red. And so the system goes in row by row and programs the pixels of the sheet. And then once it's done, it's going to move the sheet into the workspace of a magnetic coil that's under the tabletop here, right in the center. And then the coil is going to pulse a field that faces out of the screen and then into the screen. And you'll see that different portions of the pattern fold depending on when that happens. This is going to be a slow motion. So first one face folds, and then the rest of it folds. This all happens because of the way that we specifically programmed the sheet. If we programmed it in a different way, it would fold into a different pattern, right? And all of this happens in less than a second. So we've done some experiments to show that we can fold a variety of different shapes, and we can write and refold the pattern multiple times. So what you're seeing here in the video is an experiment we did where we programmed, folded, then reprogrammed, folded, reprogrammed, unfolded, and then we basically folded and unfolded this sheet like 100 times. And then we measured the strength of the magnetic of the pixels that we were writing onto the sheet, and we saw that the strength, the magnetic strength, does not change at all, even over hundreds of cycles, right? So what this means is that we can get these sheets to fold over a folding sequence of potentially arbitrary complexity. But not only that, we can then take the exact same pattern, unfold it, rewrite it, and then get it to fold into something else. So we're really excited about this because we think it means that we'll be able to get, interesting robots to self-assemble. And that requires us to put electronics on board. So what we've done is we've been working on this laminate-based fabrication approach where we take circuitry, we laminate it onto these magnetic sheets, we cut out where all of the folds need to go, we embed a mesh into the sheet just to keep all of the faces together, and then we align all of the layers, cut out the folds pattern, and then we end up with this self-folding sheet that has electronics on board. And my student decided to do this with this pattern here. This is the one that's actually getting passed around, although that one doesn't have electronics on it. This is theoretically a universal fold pattern that can fold into anything up to the resolution of these squares. But he decided that he was going to fold it into a P, and in a show of pen loyalty, light it up into the pen logo. So now what we can do is basically program these sheets in order to change into different shapes with these electronics on board. So looking to the future, what we're really excited about is basically taking the idea of origami-inspired design and then looking at how we can take advantage of the geometric design, the kinematic design, the design of the fabrication process in order to create real functional structures. One direction is, this one here that I showed you already. I skipped forward because of the question. And so we're interested in thinking about how can we take advantage of these gradient descent-based optimization approaches in order to create robots with new capabilities, potentially adding in these smart materials. We're also interested in thinking about the relationship between the structure and the electronics and actuation. And so one of my students, Dongsheng, has been thinking about, well, when we have these designs, I haven't told you anything at all yet about what are the actuators or the sensors that go on board, but all of this stuff adds mechanical complexity, it adds weight, it changes the dynamics of the robot, right? And so we've been thinking about these co-design problems where if I know what the robot's motion needs to be, I know what kind of environment it needs to interact with, but I need to also design the electronic structure that goes on board, how do I create these algorithms that can also tell me the electronics component and what are the microcontrollers, H-bridges, voltage regulators, all of that also need to support the robot so that I can design full electromechanical systems. And so he's been working on these algorithms that are iterative, that basically iterate between like the dynamical model and the electronics design in order to create these fully functional systems. And then most recently, we've been taking these ideas and then we've been embedding them into these interactive design software where we're trying to understand how it is that people approach the design process and how they think about the mechanical design versus the control complexity. So what you're seeing here then is a software that we've been working on that we call Build-A-Bot that is very simple robots that are being created in this user interface. Basically, you click and drag these 3D parts. They're all rigid. You combine them together, create interesting kinematic chains, but then we can simulate in real time for people how this robot is going to work and allow them to iterate over the design. Together with Christina Wilson, who's a psychologist at Oregon State, we've been doing user studies to see how people interact with this software. And using that information, we can now analyze their path through the design process. So we can see if we can take inspiration from what are the objectives that people care about in order to inform whatever future work that we're doing and the path of automated design as well. So that is a quick overview, I guess, an overview of all of the work that's going on in our group. I hope that I've convinced you that origami-inspired design is a valid fabrication approach for robots, and that we can actually use origami to create robots with interesting kinematics, but can also store energy and do work in various types of applications. Of course, all of this work was done by the students in the lab. I've highlighted in green here the ones who did the work that I actually talked about, and of course with the aid of many amazing collaborators. And with that, I'm happy to answer any other questions if there are any.
Thank you so much. Any questions from the audience?
Yep.
So I have a quick question about the self-folding, like the one that was passed around. So I guess I'm thinking like a lot of origami works because paper is so thin, and that is a lot thicker than paper. So I was wondering if you noticed anything with the limitations in that regard and like thoughts on that.
Yes, so there are two ways to answer that question, I guess, in terms of origami thickness. One is that practically we've been able to fold, up to 6 layers of this material before running into issues. But part of that is because of the size of the gap that we cut out for the fold, right? So if we cut the gap to be larger, we'd be able to accommodate more layers, right? And so there's a whole nother branch of origami design which deals with what we call thick origami, and that's origami design taking the thickness into account. And so I didn't touch on that work at all, but you can account for the thickness when you design the fold pattern as well.
I have a question. So it's from the same. So you said like it's like a universal folding pattern, like it can do different. So how is it controlled? Just so you said like there's a magnetic in like the coming from the screen direction and then going back. So it's just like depending on like pulse of the like how do you do different orientations?
Yes. So okay. So the universal fold pattern comment. For the pattern that's being passed around, that was not considering the actuation. Basically, it's given these folds, you can manually fold it into whatever voxelized shape that you want, where every voxel is the size of the square on the pattern. And that was a theoretical origami result from like 2015, I believe, where they just showed these folds are sufficient.
Just geometry.
Huh?
It's just geometry.
It's just geometry. Yep. And then on the actuation side, we have not yet done the full analysis to figure out, given a particular 3D shape that you want, what is the magnetic pattern that you actually program onto the sheet. All of the demos that I showed you were hand-tuned by my student, but we're working right now on taking the models that we have of how magnetic fields interact with each other on the sheet versus the external coils, and then trying to solve the reverse problem of designing the origami pattern, of the magnetic program.
If nobody else has any questions, because I asked too many.
Yep.
You can-
If you're like folding this thing so quickly, have you run into issues with like something just going wrong? Like I'd imagine like if there was like an extra bit of momentum, it might stick to something else. Has that been a large issue?
So in the patterns that we've been working on, the speed of folding has not been an issue, but you can also manipulate the speed of folding just by changing the strength of the magnetic field, right? So the speed at which the structure folds is going to depend on the magnetic force that gets applied, right? And so if you crank down the current that's going through your external magnetic coil, then you drop the external magnetic field and you drop the forces. So we can get these structures to fold more slowly if we want them to. We just haven't bothered to do it because it hasn't been a problem.
I have another question.
I think there's a question in the back first.
So in the beginning, you were talking about using precise materials and folding techniques to minimize energy loss within the system. Would it be, do you see an application for kind of doing the reverse of that and doing some sort of like optimized damping for some sort of system? Would that be applicable?
Yeah, for sure. If you wanted to change the damping of your system, you could. Practically, we have seen that when we change the geometric parameters in the fold pattern, we change the stiffness and the damping at the same time. And we haven't fully characterized the change in damping. But if you wanted to design for damping, you probably could. We just haven't done it.
Oh yeah. So it's so the build a bot program that you are using the user input data to kind of find the way. So like, who are the users? Like, it's just like grad student, college students, or
Yes, so the study, so we actually ran this study at ICRA last May. And so we pulled 40 participants from undergrads all the way to industry representatives and faculty. So we got a broad spectrum of people. We were not able to test any minors just due to, IRB.
I think it would be like very interesting, like kids do them and try to see like how they are thinking differently, like versus like trained like engineers.
Yep. Anecdotally, we have tried the software in a whole bunch of high school visitors and workshops that have come through the lab. We just haven't collected their data.
May I?
Professor Ross, yes.
Okay. Very, very nice talk. Actually, gave me some ideas. I'll tell you why. Because we are going at the design of robot from the other way, as a system.
Mm-hmm.
So I start from I want to design an arm, a gripper with some specifications, and we use any possible method to characterize the kinematics, the mechanics, and everything, and do trade-offs. And the problem we were stuck with, as we discussed at lunch and we'll discuss later on, is how do I do design space exploration with respect to geometry?
Mm-hmm.
So the question is, I can start with origami, but once I have this benchmark and show me the shape, I can actually free myself and go to other structures by finite elements like Boston Engineering has done for the redesign of the Atlas and the dog and all that, where they took for solid bones to more like our bones and so on and so forth. And then in the process of doing that, since I have now a geometry that works and I know how to search for other geometries, I can put finite elements and I can get the macro properties and go down, actuate any attempt to go that direction? I mean, or you're determined to just stick with origami? Because that's questionable, okay?
Yes. So the question is, to what extent, basically at a high level, to what extent is the origami part useful versus looking at other methods for fabricating? So to answer the last part, we're not fixated on origami. Actually, we have a few other projects in the lab where we're looking at different types of compliant mechanisms, not necessarily folded. And so I focus today on the origami because it's, they all go together.
No, it handles the geometry beautifully, and I can use this as I can use this origami-based structures as the beginning of what I do. I can go and change it, okay, and then in the meantime analyze things, right? Because, and this can help me to say what kind of geometry may be useful or not useful and so on and so forth. But then, you have other things.
And then once you have the design, you can expand to other methods. So for example, the bellows that I'm passing around, we folded, that folds in about an hour. And so now you can do very quick prototyping, but then you can also use other materials. You can make true bellows structures, et cetera, right? So yes, you can use origami as a way to prototype before you then optimize the materials or fabrication process for your design. I will say that I do think that these thin shell structures do have a place outside of prototyping as well. And we've been working on some scaling laws to try to figure out under what circumstances using thin shell structures versus solid structures makes sense. So if we take a look at like an origami robot, we scale up, the thickness of the material doesn't change, only the other dimensions change, versus a machined robot, all of the dimensions will change. And so the machined robot, your mass is going to vary cubically with the length of the robot, and with an origami structure, it's going to vary quadratically, right? And so there are different power requirements and payload capacities that result when you use different types of structures. And we're trying to do the analysis now to figure out for what sorts of tasks you want to use which type of fabrication approach.
Yeah, the other extension is totally mathematics. If I'm trying to understand geometric structure by geometry, and I go to algebraic geometry and stuff like that, I have to talk about simplicial complexes and all that stuff. I can do it over multi-resolution, which is the basis of the theorem of Bowel and all that stuff. And I can actually take that now, take your design and start varying the size of the tessels and other things and see if this gives me a structural advantage and so on. Thank you. Thank you very much.
Problem.
Okay. Thank you so much.
All right.
So
Thank you.
joining us today.